All right. Thank you everyone for joining. Hello and welcome from the Phase 3D team. Just a general note, if you do have any questions during the webinar, please use the Q&A button. Now, my name is Andrew Holliday, and I'm our Applications Engineering Manager over here at Phase 3D. Today, I'm also joined by Scott Monaghan, who is our lead software engineer. Now, here at Phase 3D, we've created a product called Fringe Inspection that is designed to enhance your workflow as additive moves away from prototyping and towards true production. Today, I'll introduce you to our technology, run you through some real use cases from our customers, and then Scott will show you some key features in one of our software packages, namely Fringe Operator. Now, the additive manufacturing industry is currently in a changing market. Companies are scaling their additive efforts as the tool is used in production applications. We at Phase 3D are focused on enabling real-time validation of the additive process to allow users to trust and to certify the parts that they are producing. Now, process variation and quality control are the main issues facing the additive industry today. Now, we as an industry need to move towards data-driven approaches to certification, inspection, and defect mitigation. In doing so, we can not only have more confidence in the parts that we are producing, but we can also reduce cost and grow the industry as a whole. Now, this is where Phase 3D has an impact. We are actively detecting anomalies as well as measuring the build in real time. This is allowing our users to make corrective actions and critical decisions sooner in the process, giving them increased understanding as well as saving valuable time and money. So, how does fringe inspection actually work? Well, it uses a process called fringe projection. And to do so, we need two key pieces of hardware, a camera and a projector. The projector projects fringes, which are patterns or stripes that are sinusoidal in nature, directly onto the build area. Afterwards, we can detect the distortion of those fringes using the camera. We can then correlate a height or a depth value to every single pixel. So to really use fringe inspection on your machine, you need those two key pieces of hardware, the camera and the projector, an angle between the two, as well as time to take the measurement. To install fringe inspection on your machine, we use existing viewports on the printer as to not modify or change anything drastically. So what does our output actually look like? Well, on the left-hand side here, you'll see a standard visual image. This may be the output from, say, the layer camera of a printer or an image-based in situ tool. Now, the issue here is images are incredibly subjective, and they are highly dependent on lighting conditions. Now, these lighting conditions and the resulting shadows can really obfuscate or hide the true impact of what is really going on within your machine. On the right-hand side, we have the output from Phase 3D's Fringe Inspection, which is a height map. Now, the important thing to note here is that we can not only detect anomalies, but we can also discretely measure them. Now, for example, you can see at the bottom of this height map, there's actually a recoder hop. Now, this is where the recoder actually made impact with the part, lifted up, then dropped down into the powder bed. With Phase 3D's system, what we're actually able to do is not only see where this recoder hop occurred, but we can detect exactly how far down into the powder bed the recoder actually went. Additionally, fringe inspection is not AI dependent, and we're not using machine learning. Instead, we're using a calibratable and repeatable measurement process, making fringe inspection actually a quality control technique. So when do we actually take these measurements and what are the main outputs from our system? Well, we actually create 3 individual height maps per layer. The first one is after a new recoder powder has been spread, and that becomes our powder height map. Now we also take a measurement after the laser has finished, and that becomes our melted height map. Now, because we take a measurement once that build platform is lowered down after the laser is stopped, we're able to generate a true layer thickness height map, showing you the actual consistency of your recoat across the entire build area. Now, each one of these measurements takes about 1 second, and we use existing dwell times within the machine as to not increase print time. Now, here's some examples of some standard anomalies that we can detect using our system. Now, of course, we can detect anomalies in the powder bed. That includes things like recoder streaks, once again, recoder hops, even short feeds, powder dropping, or out of plane distortion from part swelling. And also, because we take a melted height map measurement, we are also able to detect melted anomalies, things like spatter particles or even powder redistribution from the lasing process. Now, here's a good example of the true power of the fringe inspection system. Now, here you'll see a visual image of an entire build area. But let's take a look at the Phase 3D height map really quickly. As you can see here, there's a large streak going through the bottom row of parts. Now, if you were relying solely on visual images or an image-based solution, this recoder streak and its impact in the parts would have been entirely lost. Now, what I'd like to do is run you through a few use cases from our actual customers and show you exactly how the fringe inspection system benefited them within their process. One of our customers is an aerospace manufacturer, and what they were seeing is inconsistent part quality. A few of their parts were always having problems with porosity that were only being found during CT scanning. What the actual issue is, they had a powder dropping issue within their machine, and it was being entirely missed with standard image-based solutions like their layer camera. Now, these problems with porosity caused by powder dropping resulted in a 5% failure rate of parts throughout their entire production run and over $63,000 in wasted costs on post-processing, increased post-inspection, and even reprints. So this customer decided to install and use Fringe Inspection. It was installed on their EOS M270 in under 24 hours, at which point it was already gathering data on their builds. And what was actually found is that the recoder actually had excess powder that was building up on top of it. Mid-build, this excess powder was being dropped directly onto the part that was being printed. Now, this resulted in about 200 micron powder drops directly onto the part, which is over 4 times their standard layer thickness. So what this customer is able to do is using our Fringe Operator software, they established a 100 micron anomaly threshold. That way, anytime powder dropping or any sort of powder bed anomalies over 100 microns in height were detected, we're able to immediately flag them and alert this customer. That way, they knew exactly when to fail a print and save all of that wasted time and money for post-processing and post-inspection. Now, our system was also able to help them identify the root cause of this issue by identifying it as powder dropping onto these parts. What was actually found is a solution where they installed a blade to knock off excess powder on their recoder, as well as find the source of recoder vibrations, allowed them to mitigate this issue moving forward. In this way, Fringe Inspection was the system that allowed them not only to understand their build failures, but also make corrective actions and introduce true quality control into their process. Another one of our customers was heavily reliant on build images to assess print quality. Now, the issue here is builds are long, and it's incredibly difficult, if not impossible, to truly understand the quality of your parts only using the human eye. And what was happening is they were taking all of these build images and making videos that their quality engineers would then have to sign off on before a part was accepted. Now, this review process was incredibly long and led to a lot of issues and anomalies within their prints being entirely missed. This customer did investigate different AI solutions to aid them in this process, but they presented challenges of their own. Namely, these AI solutions were also just reliant on images, and it was difficult to find enough high quality and repeatable training data to truly trust the decisions made by AI. And even then, these AI systems showed extremely high rates of false positives and false negatives. Now, this manual reviewing of these build videos accounted for about $75,000 in labor time alone per year for their production. So this customer decided to install Fringe Inspection on their machine. As soon as it was installed, we were able to detect anomalies as well as quantify every single one of their layers, giving them a 2D and 3D view of their build and giving them full insight into anomaly shape, size, and location. But most importantly, what you'll see on the right-hand side of the screenshot is we were able to automatically generate a quality chart. Now, this quality chart alerted their engineers exactly when there is a high anomalous area or anomalous volume on a particular layer. That way, the quality engineers were able to quickly skip towards layers of interest and assess the quality of their print. In this way, the actual review time for these builds was taken down from about an hour watching these videos to about 5 minutes, thereby reducing their review costs by over 90%, as well as giving them a qualitative view to their build quality versus just looking at images. Now, our third customer was running serial production, and they were having inconsistent part failures. Despite running on the same machine, the same print file, same geometry, and even the same material, they were not getting consistent results or having trouble knowing exactly when to fail prints. All of their porosity issues were found very late in the process during inspection and CT scanning. And any sort of variability from part to part wasn't found until that. In their production run, they had about a 5% failure rate, again, with these defects only being found in CT scanning. So this customer also decided to move forward with Fringe Inspection. It was installed on their EOS M290 in less than 24 hours, at which point we're able to start collecting data on their production builds. Now, one of their print engineers was able to use the Fringe inspection data from one build that passed all of their quality metrics to establish basically a baseline golden build. Now, using the compare build feature within Fringe Operator, every single print afterwards was able to be compared to this golden build layer by layer in real time. This way, whenever an anomalous layer happened or whenever the live build was out of spec from their golden build, they were able to immediately fail it versus finding these issues later in CT scanning. What this allowed them to do was to move quickly within their production. It minimized any sort of delays caused by finding failed parts late in the process and resulted in early detection of 2% of those failed builds, saving them over $30,000 in post-inspection, post-processing costs, and even some reprints. This allowed them to really establish a true quality assurance process and give them repeatable and reliable production. Now, to show you some of these features in Fringe Operator, I'm going to hand it over to Scott, who's going to be able to walk you through what our software actually looks like and how it can be used in your workflow.
Hi, everybody. My name is Scott Monaghan. I lead the software development team here at Phase 3D. Andrew, can you see the screen okay that I shared?
Yes, I can.
Okay, great. So I'm going to walk through some of the features of this piece of software, which is called Fringe Operator. It's the visualizer, and that works with our Fringe inspection system. And it also allows for quick data analysis by anybody who is trying to figure out what's going on with the build. Now, right now, we're going to look at a build that is complete, but I just want to emphasize that this tool is designed for in situ inspection. So this tool automatically updates as the builds are going. So let's kind of just take a look at the overview of the major features. So first thing that really jumps out here that everybody wants to look at is our 3D view. The 3D view is created as the print is going layer by layer, and we detect we detect the areas of each layer that have the part on it, and then we build a stacked 3D view. In the 3D view here, you can zoom in, you can fly all around, you can admire your part, but also you can choose to show anomalies where they are in the 3D view if you want. And this build itself, was designed actually by us to have lots of anomalies so that we could show off the capabilities of our tool here. Now, the 3D view itself looks great. It gives you kind of an overview of everything. But if you really want to move into precision and start deciding whether or not you want to fail build or say that it's going to go forward, the real work in Fringe Operator is done in the 2D view, which is over here on the right. And what we're showing here is a single layer. And what this is the output of what you'd see of the true layer thickness that Andrew went over earlier, where we actually take the measurement of the powder and we take a measurement of the lased layer when it has dropped down. We do some subtraction math and we're able to get true layer thickness. And it really gives you a nice picture of your part here. But we have several channels that are available to look at here. So right now we're looking at true layer thickness, but we can look also at the powder height map if we want to do that. We can look at the melted height map. And of course, if you want to compare your height maps to what you're getting in a visual image, you can do that here by clicking on either the melted or powder image, and you can get that visual image. One thing that's neat here too is if I zoom in on this and I switch back to my height map, so let's go back to that melted height map, you can see it lines up exactly. Let's talk about a few other features that we have here that are just some features that improve quality of life for folks who are looking at this. So one thing that we have here is if you see and look up in this corner here, as I move my mouse around, I get the true measurement of what I'm looking here. So if I wanted to decide, what's going on here, I could say, okay, well, that's negative 100. It's a dip of, negative of 111 microns there. For at a higher level, if you don't want to look at the microns, but you want to do some measuring just in the XY space here, you can click on the ruler tool here and you can add, check your measurements here and get a measurement of what something is. Now this is probably, if we had an anomaly, we could measure the anomaly, and we can leave these on here. And similarly, one thing you can also do is if we've got those measurements on there and I switch over to, say, the powder height map, they're still on there and we can kind of see where things are going. This measurement feature is just a convenience feature. Now, if you saw some of the early pictures of in the slide deck of our tool, and versus some of the later ones, you might have noticed that there was a red-blue tint to what we were seeing here. But what we're seeing here now is just we're seeing yellow, red, and orange. And actually, let me switch to another layer to make this more interesting. So now we're looking at this layer and we can see we've got these discrete color bars that allow us to see areas in color ranges. So right now we're in this view, we're saying, okay, everything from 40 microns up to negative 40 microns, we're not super interested in that because in whatever part we're building, we know that, we're not too concerned about that. We want to see things that are above 40 outside of range, and especially, as mentioned before, anything over 100. And just as Andrew mentioned in the presentation earlier, you can see that powder ended up deposited here where it's not supposed to be. And so maybe I say this is out of spec for my build, and this would cause me to fail my build. This discrete color bar feature is going to be available in our Q3 release for Fringe Operator. That's what we're really excited about. I think that covers most of what's in the 2D pane. And I want to move over to the quality chart and our anomalies pane here, because this is, I think, the most useful part of our tool. Now, as Andrew mentioned in his presentation, we were able to reduce, an hour job of going through a video with not great results to a 5-minute job of someone scanning and taking a look at the build and trying to decide what they want to do. And what we have here, this chart shows the anomaly volume area in cubic millimeters. on every single layer that we have here. So you can take a quick look and see, okay, we've got obviously have a problem here, but wait, we definitely have a problem here. Let's take a look at what's going on. So taking a look here, you can see we've got some serious streaks, some serious hops, and then over here on the left, we've got a short feed happening that is also that's causing problems here. If we go ahead and switch over to the true layer thickness of this, you can see that all of these anomalies are definitely interacting with the part. So, if this were my build and we were at layer 50, I would say, okay, we need to stop this because we're definitely going to have problems. Another thing, let's see, we can also flip. There's a switch here that we can highlight anomalies that were detected here if they're not as obvious to your eye as right here. In addition to the the quality chart, which is really the quickest way to check with problem layers, we also have a full anomaly list on here that you can filter by, the minimum average depth, minimum volume, to be able to say, hey, do I want to see a very large number of anomalies that are detected, or do I just want to focus on the anomalies within certain ranges? And then within the anomaly chart, you can go in, and if you wanted to, as a user, you can add notes and tags to certain anomalies detected. So I added a tag here just to mark this in red as bad and said, hey, look, there's a large short feed on this layer. And we can jump over here to, probably want to go to the powder height map. And we can see this large short feed coming in over here. So those are the main features that I wanted to show off a Fringe Operator. Andrew, is there anything else do you think that the audience would be interested in going over that we didn't?
No, I think that looks good. And as mentioned with those tags, you can not only tag individual anomalies, but also entire builds. So if you want to do something like the golden build that we discussed previously, you can tag one of your data sets as such.
You know what? There is one thing that I did want to show here. Let me go back to the quality chart and let me go to this really bad anomaly layer. And we'll go to the melted height map here. And so one thing that is neat about these discrete color bars is that they're not set in stone. You can set these to be whatever you want. So for my view, I like to set the purple to everything between -50 and -250 microns, because for me, that really makes the part jump right out. You see the part in purple. Well, I also set anything below 250 as red, and anything below 100 above 100 microns as red. But if we wanted to, we could change this to anything that you want. So we could change this to anything above 50 microns, and it will update for you depending on what you're doing in your build. And that's really the cool power of the discrete color bar display. Sorry, Andrew. I just realized I forgot to go over that, so I wanted to show it to everybody. Back to you.
No, it looks great. I think we have a couple questions. So one of them is what systems and technologies is Fringe Inspection available for? Well, we really work with every powder bed based printer. So really laser powder bed fusion as well as binder jet. In terms of laser powder bed fusion, we work with most major machine manufacturers, including EOS, Concept Laser, Renishaw, DMG Mori, and even things like the Economy system. We also work with binder jet. We have done some cold spray work as well. And we have additional question on really data size and data storage. Scott, can you comment on that, any?
Sure. What was the actual question? I just don't see him in front of me. You read it
Yeah,
out for me?
what is our typical data size for a build or for an individual layer?
Mm-hmm. Well, I'm an engineer, and so I always answer, well, it depends. But in general, depending on the customer's preference, we can have an individual layer be under 100 megabytes of data per layer that you want to save. Or if you want to save all the data that is, picked up by our system, you can decide, okay, you know what? I want a gigabyte of data per layer. Now, most people, that's not what they would be interested in. Most folks are just interested in the height map. So it would be under 100 megabytes of data per layer.
Great. Do we have any other questions at this time? Perfect. With that, we want to thank you for joining, and a big thank you from the Phase 3D team. And we're excited we're able to show you our technology today, as well as some use cases and our software. Feel free to reach out to our team. One second, we do have one question here. What is the resolution of the camera? So we actually offer a few different resolution options. Basically, our standard resolution on something like an EOS M290 is about 100 microns in the XY. However, we do offer a higher resolution option, and that can get as low down as about 50 microns in the XY, or even lower if need be. But really, our standard resolution is about 100 microns, and we can go to higher resolution systems from there. Great. That's it. I just want to once again thank you all for joining, and feel free to reach out to me or to Noah Mostow, who's also on this call, with any sort of questions that you may have, or if you are interested in the fringe inspection system.
Hey, Andrew.
Yes.
Hi, this is Dean Bartles. I saw Noah this past weekend in Colorado. Hey, I'm just curious, have you guys used this system on fused filament fabrication to measure the thickness of each layer that's deposited?
No, we have not. However, really, to be honest with you, there's no reason why we couldn't. A lot of our installs are really based on application where the industry is moving, and the high resolution and inspection qualities of our system really lend themselves well to laser powder bed fusion and binder jet.
Sure.
However, I really don't I don't see a reason why we couldn't, and it'd definitely be an interesting application moving forward.
All right, good to know. Thanks.
Yeah. Great. Perfect. Well, thank you very much. And once again, you can reach out to me or Noah with any additional questions. And it's great seeing y'all, and excited to present our technology. Thank you.
Thank you.
Thanks, everybody. We do have one more question there, Andrew.
Let's see. So our question is, what's the difference between using a projector over a 3D scanner? Is that correct? We will, we're going to end this webinar right now. However, I will send you an email regarding some key differences between our technology and using something like a 3D scanner. So thank you very much, and I'll be reaching out.